So this video is going to be about how eigenvectors and eigenvalues are used to solve systems of differential equations. If you're interested in a specific topic or there's something specific you're having trouble with, in the description I have links to different parts of the video that talk about different things. I'm going to go over finding eigenvalues, finding eigenvectors, repeated eigenvalues, complex eigenvalues, and the significance of the signs of eigenvalues and phase portraits. So in the description you can jump around. Most of linear algebra has problems in this form where they have a matrix times x equals x prime, and you can also write that like this, and then multiplying all that out you see it's a system of differential equations. Eigenvalues, which are often represented by lambda, are numbers that you subtract from the diagonal entries of an n by n independent matrix that will make it dependent. The determinant of a dependent matrix will equal 0. This is why to find lambda, you take the determinant of a matrix, A minus lambda I, and set it equal to 0. Eigenvalues are necessary for the existence of eigenvectors, because eigenvectors are vectors that make up a basis for the null space of the matrix. And an independent matrix has no vectors in its null space besides the trivial vector, the 0 vector. There are cases where you start with a dependent matrix. When you start with a dependent matrix, your eigenvalue will be 0 because you don't have to subtract anything from the diagonal of this matrix to make it dependent. It already is. And because it's already dependent, it already has vectors besides the 0 vector in its null space. So it already has eigenvectors. Here's an example of a 2 by 2 matrix I'm calling A. You start by taking A minus lambda I, which is A minus lambda times the identity matrix. You end up with this new matrix that I call A minus lambda I, and we want to find some value lambda that will make this matrix dependent. So we take the determinant of A minus lambda I and set it equal to 0. Take the determinant, 2 minus lambda times negative 6 minus lambda plus 7 equals 0. Do some algebra to find lambda, and then you end up with 1 and negative 5. Eigenvectors are basically a basis for the null space for the matrix that you created after you subtract lambda from the diagonal components of your initial matrix. The eigenvector multiplied by your matrix A minus lambda I will give you 0. This is why you have to use A minus lambda I. This is why you must subtract some value from the diagonals of your initial matrix, because you usually start with an independent matrix, and an independent matrix has no null space and therefore has no eigenvectors. So now I'm going to show how to find eigenvectors. This matrix A, we have its eigenvalues now, so we're going to choose one to start with. I'm going to choose 1. And what we do is we take that eigenvalue and plug it into A minus lambda I to give us a new matrix that will be linearly dependent. As you see, I plugged it in and end up with this new matrix 1, 7, negative 1, negative 7. And as you can see, the second row is a multiple of the first row, which makes this matrix dependent. Next, you want to row reduce to find the null space. This one is easy. You just take row 1 and add it to row 2 and send that to row 2, and you will end up with the second row being all zeros. Whenever you row reduce a 2 by 2 dependent matrix, you are going to end up with the second row being all zeros. Now that it's reduced, you will notice that there is a pivot column and a non-pivot column. So this non-pivot column indicates a free variable. Now you have A minus lambda I set up times this vector, which is going to be the eigenvector, and you set it equal to 0. And what you're looking for is a vector you would multiply this matrix by so that it will equal 0. We know that our second component of this vector is 1 because of the free variable. And then you choose the first component depending on what would make it 0 when it's multiplied by. So negative 7 is the choice, and as you can see, if you multiply this matrix by our eigenvector, negative 7, 1, you end up with the 0 vector. So we have found -7, 1 to be our first eigenvector. Now that you've found the first eigenvector, you want to use the second eigenvalue to find the second eigenvector. So you would want to do the same thing as you did with 1. You would do a minus lambda I, where lambda is -5 this time. You end up with this new matrix, 7, 7, -1, -1. Next you want to row reduce. This one you row reduce by doing 1/7 times row 1 plus row 2 going to row 2. And once again you end up with zeros as the only components for the second row. You have a pivot column and a non-pivot column in your row reduced matrix. You want to set it up so it's that matrix times a vector equals 0, because we're looking for a vector that is the basis for the null space, which is the eigenvector. So this non-pivot column tells us that the second component of our eigenvector is 1. Choosing -1 as the first component of the eigenvector will make it multiply by that matrix and give you 0. You can check your work by multiplying that eigenvector by the matrix to see if it gives you the 0 vector, and it does. So you know that this is your other eigenvector. Once you have all of the eigenvalues and eigenvectors you need, you can plug them into this formula right here, and you will have the solution. Sometimes when you're finding your eigenvalues, you'll end up with a repeated eigenvalue. This isn't necessarily a problem if you have a unique eigenvector for each eigenvalue. So if you have a 3 by 3, and let's say you get 3 eigenvalues, and 2 of them are the same number, as long as when you take a minus lambda I for that specific eigenvalue, and you end up with a rank 1 matrix that has 2 non-pivot columns, it's okay, because you will get 2 different eigenvectors because the dimensions of the null space is 2. And so you will get 2 unique eigenvectors for those 2 eigenvalues, which is fine. Here's a quick example of a 3 by 3 case where having a repeated root really doesn't affect you at all. This 3 by 3 has eigenvalues 2, 2, and -4. For -4, you would find your eigenvectors the usual way. That's not interesting. Here it is, 1 through -2. But for 2, you would plug it into a minus lambda I, and you end up with 1, -1, 2, 3, -3, 6, -2, 2, and -4. Then you would row reduce. You would start by doing -3 times row 1 plus row 2 to row 2, and it becomes 0. Then you want to get rid of row 3, and you do that by 2 times row 1 plus row 3 to row 3, and you end up with 2 rows of just zeros. This is a good situation. You have no defects, and that is because the dimensions of the null space are 2, which means you'll have 2 eigenvectors, 2 vectors that are a basis for the null space. You have 1 pivot column and 2 non-pivot columns. And then you just find those 2 vectors for the null space, which you know you do by first assigning 1 to the free variable spot, which are decided by where the non-pivot columns are. Then by default making the free variable you're not using for that specific vector 0, and then just filling in the first component depending on what would multiply to make everything 0. If you'd like, you can always check your solution by multiplying each of your eigenvectors by your row reduced a minus lambda I to check and make sure that you get 0. Then you just write your solution the same. The only difference is 1 lambda will be repeated, but otherwise your solution will be pretty normal. What you'll end up with if you have a 2 by 2, every time if you have a 2 by 2 and it has a repeated eigenvalue, you're going to end up with a defect, which is where you don't have a unique eigenvector for every eigenvalue you have. And when this happens, you have to treat the problem slightly differently, and I'm going to go through an example that shows that. You'll start this problem normally by trying to find your eigenvalues, doing so by taking the determinant of a minus lambda I and setting it equal to 0. After some algebra, you notice that your two eigenvalues are the same number. Next, you plug in 4 into a minus lambda I and row reduce as you usually do. You do that with negative 1/2 times row 1 plus row 2 sent to row 2, and you get zeros as all the components in your second row. This is when you notice there's a defect. You have one pivot column and one non-pivot column, which means the dimension of your null space is 1. So you're only going to get one eigenvector, even though you have two eigenvalues. This is a problem. You find your first eigenvector normally by choosing 1 as your second component of it due to the pivot column, and then choosing 2 because that is what would multiply by the matrix to give you 0. To find your second eigenvector, you take your a minus lambda I before row reduction, and then put some vector in and set it equal to your first eigenvector. Our original eigenvector has 1 as its second component due to the pivot column and the free variable it has. Our second eigenvector is going to have 0 in that free variable spot. Then you choose your first component to be a number that when multiplied by your a minus lambda I will give you your first eigenvector. For this particular problem, that number is -1. You can also check your work by multiplying it out, and you will see that it gives you your original eigenvector. Now you have all the information you need to set up the solution. This solution is going to have its first term be the same as a usual solution with your eigenvector and e to the lambda t, but your second term is where it's going to be different. What you get is your found second eigenvector plus your first eigenvector times t. I like to simplify my answer, so the second term is written as one vector. Now I'm going to do an example of a situation where you have a 3x3 that only has one eigenvalue that is all repeated, that ends up having two defects, meaning there are 3 eigenvalues and only one eigenvector. So I'm going to start with this matrix and do the usual thing where you take a minus lambda I, take the determinant of that and set it equal to 0, and then solve for lambda. For this one you have 2 as the repeated eigenvalue. So you plug 2 into a minus lambda I and end up with this new matrix. You don't have to, but I switched the rows around to make it look more similar to matrices we're used to. There are 2 pivot columns and 1 non-pivot column. That means that there's only going to be one eigenvector because the dimension of the null space will be 1, since there's only one non-pivot column. This gives us 2 defects, and this is an issue. You find your first eigenvector the usual way by taking your a minus lambda I and setting it equal to 0 with some unknown vector that it's being multiplied by. You then choose the free variable, in this case is the third component of the eigenvector to be 1, and then you choose your other 2 components depending on what would make things 0. Choosing 0 as the top component and 3 as the second component will give you 0 when it's multiplied by that matrix. You can check your work and multiply it out yourself and see that it does give you the 0 vector. So this is our first eigenvector. Because your matrix was rank 2 and only had one non-pivot column, to find the other 2 eigenvectors you have to do a different method. To find the second one, you take your original a minus lambda I before you did the row switching, set it equal to your first eigenvector you found with some vector in between. Just like in the 2x2 case, you will make the original spot where there was a free variable that gave you 1 for your third component of your original eigenvector, you will make that 0 for your second eigenvector, and then your other components will be chosen by what will multiply by that a minus lambda I to give you your original eigenvector. Multiplying a minus lambda I with 0, -1, 0, you end up getting your original eigenvector. So this is your second eigenvector. To find your third eigenvector, you take your original a minus lambda I again, with some mystery vector being multiplied by it and set it equal to your newly found second eigenvector. There's no trick of making certain components of it 0 like there are for finding the second eigenvector. You just look at it and see what components it should have so that when multiplied by a minus lambda I, you end up with your second eigenvector. If you multiply a minus lambda I by 1, 0, 0, you will end up with your second eigenvector. So 1, 0, 0 is your third eigenvector. Now that you have all the components you need to write out a solution, you do your first term, which is going to be usual, because that eigenvector was not found from a defect, it was found naturally. It is a basis for the null space for a minus lambda I, so you just put that vector in with e to the 2t. Your second eigenvector was found from a defect, so it's going to be written differently. You're going to have your second eigenvector plus your first eigenvector times t, with e to the 2t on the outside. Your third term includes an eigenvector that was found from a defect, so you take that third eigenvector and add it to your second eigenvector times t, and add that to your original eigenvector times 1/2 t squared. Next, you can simplify your solution so you end up having only one vector in each term. Occasionally, when you're solving for your eigenvalues, you'll end up with complex numbers. This is not an issue, and you can solve the problem pretty easily with a little bit of memorization. I'm going to do an example with this matrix right here. You start by doing your usual a minus lambda I, taking the determinant of that, setting it equal to 0, and solving for lambda. When you solve for lambda, you see that you end up with a pair of complex conjugates. You treat this usually and take one of those complex conjugates and plug it into a minus lambda I. This is when you start treating things differently. You could row reduce this matrix, but it would be a huge hassle and there would be a lot of room for making arithmetic mistakes. Remembering that usually with a 2 by 2, you end up row reducing and get a row of zeros as the second row, you can take a look at the first row and choose your second component of the first row to be your first component of your eigenvector, and then choose the first component of the first row to be your second component of the eigenvector. Then you must negate one of them. I chose to negate the -3 minus 5i. You could have easily just made -17 positive. You could find the second eigenvector the same way, but it's a lot of work, and there are two formulas you're given that you can just plug your first eigenvalue and eigenvector into to give you your solutions. So all you really need is your first eigenvalue and eigenvector. Once you have them, you look at your two formulas. These formulas take into account the fact that your eigenvectors and eigenvalues are complex conjugates, and so all you have to do is input your first eigenvalue and eigenvector into both of these to get your correct solution. Alpha represents the real component of your eigenvalue, and beta represents the imaginary part of your eigenvalue. Correctly inputting the real and imaginary components of both your eigenvector and eigenvalue into these formulas will end up giving you your solution. Next, you can simplify each of your terms so that they have just one vector in them. Last, you add both of your terms together to get the full solution. The significance of the signs of these eigenvalues come into play when thinking of the long-term effects of the systems of differential equations, which usually describe a consistently changing real-life situation. Positive eigenvalues indicate an infinitesimal increase of whatever is being described by these equations. These result in a point source with lines stretching to infinity that favor the eigenvector with the largest positive eigenvalue as time goes to infinity. Negative eigenvalues indicate an eventual drop to 0. This results in a sink with lines all going towards 0. The lines favor the eigenvector that has the smallest negative eigenvalue as time goes to infinity. A positive and negative eigenvalue indicate a saddle. A zero eigenvalue indicates a steady state solution. That means as time goes to infinity, the conditions of that eigenvector stand. Complex eigenvalues that have a real component alpha of 0 will have a phase diagram that looks like an ellipse. Complex eigenvalues that have a positive real component will have an outward spiral, while complex eigenvalues that have an alpha that is negative will have an inward spiral. So I hope this video was helpful, and if you have any questions or anything you specifically want to see, just comment, and I hope you get a really good grade in your linear algebra or differential equations class.